That's one a difference. In the straight two-phase locking, in the base version of this protocol, it says all locks held by a transaction are released when the transaction completes, meaning when transaction commits, either commits or aborts, by the way. When transaction commits or aborts, you release all the locks you have acquired so far. That's straight two-phase locking. The non-straight two-phase locking says the following: the way you acquire lock is the same, but the way you release locks is slightly different. What it says is you actually can release locks anytime. You don't have to wait until you commit or abort to release locks. However, this is important. However, you better know what you're doing. Meaning, once you start releasing locks, you can no longer acquire any new locks after releasing the first lock. You cannot acquire any new locks after releasing the first lock. You may wonder, hold on a minute, what's really the difference between the two? What's really the difference between the two? Well, the point is, the first version says you release lock all at the same time. You may have hundreds of locks. You release all of them at the same time. The second version says, you know what? As long as you have acquired all the locks you need and you're done with some of your locks, you can release those first while holding on to some other locks. So I may still hold a shared lock on B, but I'm done writing the value A, so I can release exclusive lock A right away, rather than wait until you commit. There's a huge difference, by the way. Let me illustrate that using a simple example. Okay? There's a huge difference of the two. So let's say I want to do the following. I do share lock on A, and then I will read the value A, and I can proceed. Now this guy tried to obtain an exclusive lock on A and to write the value A, potentially to write the value A, but this will be obviously blocked. Because of this, you cannot proceed. You cannot proceed. Now, this guy said, I'm gonna, once I know the value of A, maybe I use the value of A to compute the value of B to update, right? So I will do something. So I do something here. So that's CPU cycles. Then come back, say I will write, obtain the exclusive of B, and try to write the value of A. You know, but and then I will do something else. I will. And suppose it's a sequence of operations, I update these guys one by one. But note that since you are still holding the shared lock on A, while you are doing all of this guy cannot proceed. You want me? Yes? So straight two-phase locking says, when I commit, this is when I release what? This is when I release all the locks. So only after I commit, I will be able to, this transaction will be able to acquire that exclusive lock and proceed. You follow me? This is strict two-phase lock. So far so good? What about non-strict two-phase lock? Well, this is still okay if you are non-strict two-phase lock, because once you release lock, you do not acquire any new lock, so it's okay. However, I can do better than this. What I'm going to do is, right before I do that, right before I acquire the lock on, so what I will do is, instead of doing this, what I will do is do this. Before I do the write of each object, I will acquire all the locks I need. Maybe writing to this object takes a long time. So big object takes some time. So I will acquire all the locks before I start writing to any one of them. For non-strict two-phase locking, allow you to what? Because you know at this point you no longer need to acquire any new locks. And then this guy can immediately see right here, rather than wait until then. And then you can proceed with. And at that time you can release the other exclusive lock. Another alternative is to release you release the lock immediately after you're done with it. But one thing to note is that you cannot release, you cannot do this though. You cannot say release here and to allow WA to proceed right here. This is not okay, even in straight to this lock, even in non-straight to this lock. Why? Because you are still acquiring new locks after you have released locks, which is not okay. So that's the subtle difference between the two versions. Do you understand?
So, question.
Yeah.
So does that mean that you can only release it once, or
you can release multiple locks, but the point is, after the release of the very first lock, you can no longer acquire any new locks. There are no restriction on how many locks you can release before you commit. But once you start releasing locks, even just one, you no longer can allow to acquire any new locks. Whereas in straight to this lock, it's much simpler. You can acquire locks as much as you want, as long as it's compatible by other locks, held by other transactions. But you only release lock when you're ready to commit or abort. You don't release locks before that at all. So what's the difference? Now here are the important claims. Straight two-phase locking allows only serializable schedules. And it does not introduce cascading abort. So it only allows serializable schedules and does not allow cascading abort. What about non-straight two-phase locking? Non-straight two-phase locking says it also only allows serializable schedules. But at the same time, it may introduce cascading abort. So that's the subtle difference between the two. So I will skip this because I talked about this already in the class. I will use this figure to demonstrate to you the difference between straight two-phase locking and non-straight two-phase locking. Okay? So straight two-phase locking says, by the way, y-axis is number of locks you have obtained, x-axis is time of the execution. In both cases, there is a growing phase, meaning you are acquiring locks. So that's why the number of locks keep going up. And then you do some computation. Well, you can do computation even while you are still acquiring locks. So computation can still be carried out here. But for straight two-phase locking, the number of locks goes to 0 immediately, only at the time either commit or abort. So this curve looks like this. What about non-straight two-phase locking? There's a phase you acquire more and more locks. You do computation. This is the time when you first start releasing lock. This is the time when you release the very first lock. And once you do that, the curve is going to go down because the number of locks is going to reduce. The point is, once you go down, can you go up? You cannot go up. You have to go down all the way. It could be a general case of that is maybe looks like this. You compute, you reduce, stable, come down. But you can never do something like that. Paradox, down, go back up. That's not it. But for straight two-phase locking, it's always going to be like that. In both cases, you cannot, in the growing phase, you cannot come down and grow again. These are not okay for both cases. Okay? And the bottom line is both protocols allow serializable schedules and but non-strict two-phase locking may permit cascading abort. So aborting your transaction. So how do you abort a transaction? So, okay, let me talk about this and I will stop. Okay. If transaction Ti is aborted, all its action has to be undone. So how do you undo a transaction? Well, you use something called log. We will talk about that in the next lecture slides. So log is something that you keep around on permanent storage media that remember what has been done by a particular transaction. Not only that, if Tj, another transaction, reads an object last written by Ti, then Tj must be aborted as well. Essentially, you are reading an uncommitted object. That's why Tj must be aborted. So with this being said, Tj, the abortion of Tj may in return lead to rollback or abort of another transaction. That particular phenomenon is called cascading abort. Strict two-phase locking does not allow cascading abort. Non-strict two-phase locking may allow cascading abort, but both only allow serializable schedules. Okay? So there's a short discussion of log. I will skip. Now, before I proceed, I will stop right here. Yeah, question.
Like T1, if it gets blocked, does it just wait until it's unblocked, or?
Very good question. So, if T1 is blocked, should T1 just wait or do something else? In the case T1 waits, is the wait indefinitely long or something? And this goes to the topic of what we call deadlock. I will show you really quick. So for example, it's possible T1 is waiting for a log held by T2, T2 is waiting for a log held by T3, and T4 is waiting for a log held by T2. So far this is okay, because as long as T3 releases the logs, T2 can proceed, and eventually T2 will release all the logs, and T1, T4 can proceed. So this is okay. But imagine T3 says, well, I realize I need to prepare logs that's held by T1 on different objects, right? T1 is waiting on A, T2 is waiting for B, and T3 is waiting for D that's held by T1. Now what happens? Nobody can proceed. Nobody can proceed. And this is called deadlock. And that goes back to your question essentially. Unfortunately, I don't have time today. I will resume the discussion on Thursday. Before I let you go, I mentioned to you already, tomorrow I have to go for a meeting at DC. I come back on Friday. I could just cancel the lecture on Thursday, but I feel like we just don't have the luxury of canceling lecture at this moment. So I will ask my PhD students to come and do the lecture on Thursday. Robert and Joya will be here. And they know this stuff really well. They actually write transaction engines. So you know this stuff really well, so they should be able to do a very good job on Thursday. Okay? See you on Thursday. Homework is due on Thursday, okay?
So we bring it to class and give it.
Give to the PhD student, my PhD student, then they will pass to me. Even though